Welcome back, everybody. So this is now lecture number 8. We will continue now the discussion of the topics as per the syllabus. So I've prepared the syllabus. Please keep in mind that the research notes number 1 are essentially due on 10/31, so that's next week Sunday. And we have now 10:24 today, so by the time you're seeing this, it's 10:25. We are now moving forward. So we have now finalized linear regression, essentially in broad strokes. So you have now homework 1 submitted. You have been assigned the research notes. You're working on the research notes. You have by now taken the exam number 1. So you have basically made your way already through most of the assignments for this part of the entire class. So for this very reason, we will now continue into a new topic. So we will be talking about logistic regression today. We will specifically talk about the introduction to the logistic regression. We will talk about odds ratios and the interpretation. We will be talking about the relationship between a 2x2 table, a contingency table, and the logistic regression, and the odds ratios calculated from a 2x2 table, and the odds ratios derived from a logistic regression. We will also talk about the interpretation of predicted probabilities. This will be done basically on examples that are being in the slides of Professor Sang, which basically include the RCT data from the HELP RCT, which essentially we discussed earlier. Sorry. How do I hold it? Sorry about that. Which is basically the HELP RCT data that essentially we have seen earlier. For the lab, we will be talking about the Challenger O-ring data, which basically is an analysis based on data from the NASA on the Challenger catastrophe from 1986. This is the example that from Professor Sang that he had included in the lecture. Again, research notes are due on 10/31, and we continue our journey then to effect modification, MLE, in logistic regression, specificity, sensitivity of the predictions, including the receiver operating characteristics curve. This is going to be pretty cool. Then propensity score matching. Again, a very important and very state-of-the-art topic. It's a very popular method. In fact, it's increasingly in the literature. Then mediation, analysis, classical modern approaches. And lastly, we will be talking about missing data as a concept and how to handle this. We will also talk about multiple imputation. Good, okay. Enough about what else will be on the menu. Let's talk about logistic regression. So again, please download all the files as usual. Please copy them in the lab and the lecture folder on your desktop in the respective class folder. Just makes it easier to keep an overview. Good. We are now starting. Okay. So, and again, I didn't share the screen. So I hope you followed along with what I was showing. Sorry about that. So I basically just walked through the syllabus. There was nothing else that I showed. Okay. So, but now you should be seeing the screen. Again, we are talking today, this is class 1. We are talking about, don't take the slide from here. Okay, so class 8, basically we will be talking about logistic regression. specifically about modeling a binary outcome. So far, we talked about linear regression, and in linear regression, we essentially have a normally distributed continuous variable on the left-hand side, and we have on the right-hand side covariates predicting and affecting the means of this predicted yi. So now when you have a binary outcome, you have a condition like a 0 or 1. You get a whole different scenario. So firstly, the data is not normally distributed and it's not a continuous variable, logically. So we will do this comparison and we will see how we model the mean of that predicted yi. And the question here still, yes, we are still modeling a mean, and you will see why. And this is essentially the fascinating bridge between linear and logistic regression as a regression method, very fascinating, and you will see why. So then we will be discussing the derivation of the odds ratio. We will move over to logistic regression in R, and we will see how that is being done in R. It's super easy code. The trick is really that you need to understand the concept and the basis of it to essentially be able to interpret it correctly. And this is where it's getting tricky. Okay, logistic regression in R, we're calculating a predicted probability based on that model that we have developed, and then lab 8 is going to be the second part of today's class. So we are modeling a binary outcome. That means that we essentially were interested in binary outcome that is either a 0 or a 1. And that can be literally everything. Everything that you think of that is an outcome of interest. It can be linked with a primary physician or not, like in the HELP RCT dataset that we will be using as an example. It can be flu shot status, COVID-19 vaccinations, success or failure of space shuttle launches as in the lab. And the data can have a form basically as shown here in 0 and 1. So again, how to visualize this on a data basis, on a data space basis. So when you think of data, you basically will have row by row by row outcome, right? And the problem was, and this is one of the problems with logistic regression, you really cannot accommodate censoring. Censoring meaning that you have, for example, you're observing an outcome over a period theta of 1 year or 6 months, and you have outcomes happening. So you will basically assume that the probability of that outcome is not changing in a way. So you're just observing it over a predefined period of time. So you cannot account for individuals dropping out. Meaning okay, let's put it in that way. If you think of probability is calculated successes in a number of trials, right? So you have success divided by trials. You have rolling a 6 on a die, and you rolled it 1,000 times. Your probability is gonna be 1/6 multiplied by 1,000. So so you have independent events, and the probability each time is going to be 1/6. So now, if you would, for example, you're rolling that die only 500 times, and then you scratch off, I don't know, you scratch off one of the numbers, suddenly the denominator will be changing. So it's not 1/5 anymore, it's not 1/6 anymore, it's 1/5 now. And this happens for the second half. So obviously this will affect the probability and the constancy of the probability over time. So this is what I'm talking about, right? If you have individuals that just like, they don't die, but they don't go into hospital, they just, I don't know, they move away and you can't follow them up anymore. So your probability changes for a certain period of that observation period. So this is a downside of logistic regression. So this needs to be kept in mind whenever employing logistic regression, but more about that in BIOS 2. I'm just giving you a heads up that this is something you need to keep in mind. So, but basically it's the easiest form. You just have a probability that is based on a binary outcome. So you have the yi on the left-hand side is a 0 or a 1. On the right-hand side, you're trying to model that probability. So yi is 0 and 1, and there are certain use cases where you can use that. And one of the outcomes, for example, gender, can it be an outcome? That's a tricky one. So firstly, an outcome in principle is always defined as a result of an action or result of a process. Can it still be an outcome? Well, in propensity score matching, we're probably going to go in that direction. So you're defining it as an outcome in the selection process of the population. But again, generally spoken, for this typically use case scenario, it's not an outcome, because it's basically it's a characteristic of a certain constituent of a population. So it's not an outcome per se of an action or a process. So an outcome should really have a preceding kind of predicting, should have predicting covariates, like hospitalizations would be predicted by bad general health, or by cigarette smoking, or by, I don't know, love for skydiving. But you see where it's going, right? Covariates predict outcomes. Good. So gender not per se to be chosen as an outcome. So now the use cases. When do we use logistic regression? And this is where we're basically coming back to the various scenarios, right? So we have, and you have evaluated these methods already in your early education. So you have example 1 here that's listed by Professor Sang, where we have xi is a binary variable. So we have treated or control and homeless status. What essentially would that imply? Well, it's essentially somewhat a 2x2 table. You can calculate essentially odds ratios ordered by this 2x2 table, but it is one of the use cases. Then we have example 2. We have a categorical variable with more than 2 categories, meaning we have hospitalization, yes, no, explained by education, race, etc., etc. So this is one way to look at it. All of this can be modeled by logistic regression as well. And now, what is the scenario when we have xi as a continuous variable? It's a little different, right? We will, to some extent, have the possibility to sense whether there's some form of a difference between the outcome groups by just running a 2 samples t-test. So if you, for example, you have hospitalizations, yes, no, and you just run a 2 sample t-test between those that were hospitalized and those that were not hospitalized, you essentially would get a significant difference in a perfect world scenario. But again, it doesn't allow you to adjust for confounding. So practically spoken, in the real life world, you would do that sometimes. You would sense for a pathophysiological signal. So you have patients that get hospitalized, you have patients that are not getting hospitalized. You would compare their age, classically predictive hospitalization. So you compare the age and you say, okay, so my hospitalized group's older. I predict, or I think, that age is a predictor. What do I do with this knowledge? Well, you keep that in mind when you construct your predictive models. So for this very reason, is it appropriate? No, because it doesn't allow you to see a clear association and a quantitative relationship. Does it give you kind of a binary idea about whether there's an association or not? Hypothetically, not taking into account interactions, not taking into account confounding, but yeah, it may give you hypothetically an idea of what may be predicting outcome. So, but generally, is the 2 samples t-test appropriate to establish this relationship? No, it's not. But how can we do that? So we have looked into linear regression where the yi was continuous. So we had, for example, with blood pressure predicted by serum glucose, our classical example that we have repeatedly looked at. So we had, for this prediction, we had yi on the left-hand side, our predicted outcome, which was essentially systolic blood pressure in a continuous fashion, and predicted y hat equals a beta 0 plus a beta 1 xi plus an error term ei. So now ei was, and we have seen that, basically normally distributed, the residual centered around the mean of 0 with a variation of sigma squared. So this equation 1 can be rewritten as well as yi equals a normally distributed beta 0 plus beta 1 xi and that error term. So the covariates do essentially affect the yi by predicting and affecting the yi's mean, the predicted mean. So using the same idea for a binary yi basically allows us to now use, instead of a yi, which is that mean of that yi in a linear regression, it's being replaced with a Bernoulli distributed probability of I. And the probability of I is the probability of an event. So how to think of that? And this is where I really want you to probably go back to your introductory statistics slide and look up the binomial distribution. If you have a binomial distribution, you essentially, under the law of large numbers and the normal approximation, you can always say that the probability of an event is basically to be considered equal to the prevalence of a condition in a population. Remember that? So you have 10% diabetics in a population. Your probability of picking a diabetic from a random sample is 1 out of 10 or 10%. So this being said, you have the Bernoulli distributed PI becomes now your outcome. So the covariates are then essentially a Bernoulli distributed beta 0 plus beta 1 xi. So basically it is a covariate predicting the chance or the probability of the yi being 1, of the yi being diabetic yes no. What's the probability of picking a diabetic? And we're predicting that by our Bernoulli distributed beta 0 beta 1 xi. It's pretty simple so far. Good. And the mean of yi is set equal to probability of I. And the probability of yi equals 1 is then essentially diabetic yes no. Oh, diabetic yes, not no. So it's diabetic yes over diabetic yes and diabetic no. Denominator, numerator, denominator. Good. So we're denoting PI as the probability of yi equals 1. So the probability of yi equals 1. So now hypothetically, you could say, okay, so I'm assuming now that the probability of I is essentially equal to beta 0 plus beta 1 xi. Can we really say that? No. And why not? So there's one particular reason. Sorry, I'm just making sure I'm borderline sitting in the always want to make sure that the recording is actually switched on, because I have given once another lecture that didn't record. Okay, good, but we're on. We're recording, so you've heard all my rambling excursions here. Good. So what are the problems now with this? So we have PI equals beta 0 plus beta 1 xi. What potentially could be a problem? And really take a step back and think about it before I give you the answer right now. If we run an in-person class, I would try to get this out of you right now. But the problem is quite logical, because when you have a probability, you have, this is equal to a percentage, right? And there's, when you think of a probability as a percentage or as a proportion, you essentially have the proportion only reach and taking a possible value between a 0 and a 1, or a 0 and 100 for percentage, whatever, if you multiply by 100 or not. So this being said, it's limited. However, when you think of beta 0 and beta 1, xi, this is essentially reaching up until infinity. So this is where a problem occurs, and you're getting into an arithmetic problem here, which I'm not going to go deep into this because I don't think I'm qualified to do so. However, what you're doing is you're transforming your probability in something that also reaches up until infinity, negative infinity and positive infinity. So it's basically, it can have positive and negative values, and these are the so-called odds. So it actually can not be negative, sorry for that. But essentially it reaches infinity. What can reach infinity are the log odds. My bad, forget what I said about the negative. So basically you're transforming it that instead of having this limited probability, you now can also extend, just like the right-hand side, your odds to infinity. So essentially, if you are dividing the probability by 1 minus the probability, so the inverse, the probability of that event not occurring, you're basically getting the odds. So this would be, in essence, something that you also discussed in your introductory statistics lesson. So it's basically going back to the example of the die. So basically, when you have a die, you essentially would, let me find a slide in that regard. Let me find some resource. Okay, I was actually hoping I'm going to find a better example than that, but let's just, for the sake of time, let's just do that. So Towards Data Science, which is actually a really good resource, made me find something that kind of made sense. So we have the probability of head by throwing a coin and drawing heads or tails. So we have the probability of heads obviously is 50%. So 50% is like you have one success divided by 2 trials, and you basically 2 possible outcomes, and you basically get 50%. So if you are using instead the odds, and this is an example that I'm not sure, I think it was a different example in the intro slides, but basically think of it. You have the probability of win over the probability of losing. So this is probability of win essentially is here essentially being okay, I'm giving up. So there's no an example of my dreams. So let's go with an example that I found here. So you have 20 marbles in a bag, 8 are red, 6 are blue, 6 are yellow. So if you were to quantify the probability of picking red marble, your probability of picking red marble randomly out of those 20 marbles essentially would be 8 over 20, right? If you were to calculate the odds, you're looking at 8 over 12, because it's 8, the probability of picking a red one, over the event of this not occurring, which is 20 minus 8. And this is 8 over 12. So you can convert it then to 2 over 3. And essentially this would be the way to approach the odds. The thing about it is that you transform it from something that is limited, with limited bounds from 0 to 1, to something that goes towards infinity. Okay, so but let's carry on. I was hoping for a better example. Apologies for that. Okay, so we have talked about the issues. So now the left-hand side are the odds. If we divide now PI, which is our marble, those are the 8 red marbles, divided by 1 minus PI, which is 20 minus the 8. So now the left-hand side are the so-called odds. And there is essentially at this point no problem. At this point, there is only one problem left, and this is where I want to show essentially a slide from BIOS620, which I think indicates that quite well. Because the problem you're running into is that you have a relationship that is a non-linear relationship between the odds and the probability, logically, because you're having something that is infinite that you're trying to convert into something that is non-infinite and basically is restricted. So essentially this relationship you need to transform to essentially, and this is where basically the log odds come in, because essentially you have for most of that, you get somewhat a linear relationship. And this linear relationship requires you to essentially transform those odds into the shape of log pi over 1 minus pi. And these are the so-called log odds, which here, log odds as a function of probability, essentially gives you to some extent a linear relationship for most of your range of probabilities. So essentially to relate probability and log odds, you introduce what is called a so-called logit function. And this logit function essentially you're employing on the left-hand side to equate this pi over 1 to pi 2, otherwise as the odds, to your probability. On the right-hand side, you essentially have no changes at this point. However, the left-hand side now ranges from as the log odds, and this is where my minus infinity and plus infinity comes in, that I mixed up before, essentially is now on the left-hand side. So now this is a simple logistic regression model. So now you can rewrite it to essentially express again your probability I, and you would do that by essentially exponentiate the right-hand side, and by that come back to your probability. So you have E by the power of beta 0 plus beta 1 xi and 1, which is this one, plus the same exponentiated term. So the right-hand side of 3 does now go from 0 to 1 in compliance with the properties of a probability measure that you have here. So you can by that, you can calculate your probability by basically transforming your right-hand side in a way that you can arithmetically use this in the context of probability ranging from 0 to 1. I hope that all makes sense. So again, to repeat, logit function relates log odds to probability, basically forces it in a kind of a linear shape, which has a little bit of a non-linear nature, but essentially for most of it, it's considered to be linear. And thus, it's being used as a linear function. So this linear, this logit basically allows you now to express your odds as probabilities by basically exponentiating the right-hand side. So now comparing this to linear regression basically gives it kind of a comparable form. So you have in the linear regression, you have the beta 0 and the beta 1 xi plus the error term. So the error term is normally distributed around a mean of 0 with sigma squared describing the variability of the residuals. So the logistic regression is now the log pi over 1 minus pi as the log odds equals exactly the term that we have for the linear regression. So it's basically a linear relationship, relating these log odds in a linear fashion to each other. So now what's different? And again, take a step back and think about it before I'm telling you the answer right now. Press pause and think about it. What's different? Different is the error term, because you don't have this error term here. And why don't you have this error term? Because the error term is already contained in your counts, right? If you count in probability, you count success and trials, essentially your probability here contains already that error term. And you don't get this error term that you have with linear regression, where you have varying blood pressures and serum glucose values. There's variance in your data, and you also need to check for homoscedasticity. You got to make sure that the variance is equal of the whole range of observed values. This falls away with logistic regression because you have your error term contained in your probability. Yeah. So we have a variance. We still have a variance that is dependent on your sample size, but we will talk about this later. We have a variance y equals probability multiplied by 1 minus probability. So the variance basically derives from only the right-hand side. But the mean of y is basically the probability of y happening in the Bernoulli distribution. So now how do you interpret beta 1 and beta 0? So beta 1 and beta 0 are essentially the so-called log odds, right? So if you are now calculating log odds for outcome equals 1, you essentially get a beta 0 and a beta 1 that essentially in its sum represents the probability or relates to the probability and predicts the probability of that event to occur. When we are looking at xi equals 0, which is essentially the event to not occur, so that's the categorical variable where xi equals 0. We have we gotta discuss that in detail later on. So we have beta 0 and beta 1. So we have that outcome with intercept, and let's say this is male gender, we would essentially have the beta 1. So again, it's the same relationship then with the linear regression. So we have here probability I of that event to happen is here probability of yi equals 1 and xi equals 1. So this would be male gender, yes, no. Then we have pi of 0, it's yi equals 1 and xi equals 0. So essentially we have here, just like in the same fashion with the linear regression, we're basically getting the same situation. So if we are now taking into account that male gender versus female gender would essentially now relate to the log odds of the covariate male gender equals 1, so males. These would be the log odds for males minus the log odds for females, where male gender equals 0. So essentially we would now see log odds, and this is where we can then amalgamate both terms to log of pi 1 divided by 1 minus pi, and as a rule between logs, you divide subtractions within the log term. So this essentially becomes here now the so-called log odds ratio. So you need to basically then exponentiate the left-hand side to get the odds ratio per se. So how does it look like? So we have here the treatment on link status outcome from the HELP RCT data set. So we have treated yes, no, treated yes, no at link status. So we essentially have here 2x2 table. We have those that have link status yes and were treated with 128, and we have those that have link status no and were in the control group. Using this to calculate the log odds will basically get us to 128 over 94 divided by 35 over 174. So it's basically would get us now to 136 over 0.2 and to an odds ratio of 6.77, which means that those with link status yes were more likely to get treated. So this being said, so you always arrange the data-driven intervention on the rows while the outcome on the column. So this is the epidemiological way of depicting it. You will see different variations. Always make sure that you understand the 2x2 table before you start calculating and employing the formula. I'm just telling you that because in some certain respects, you may see different 2x2 tables. So there are variations between the way people are depicting 2x2 tables. Keep that in mind, particularly in the realm of data science, there are different ways of doing that. You will see that. So whenever you speak with a data scientist who shows you 2x2 tables from his machine learning or AI endeavors, they will use a different kind of 2x2 table. Keep that in mind when you employ formulas. The calculation is with respect to each row. And the ratio, either the odds ratio or relative risk ratio, and the risk ratio, the relative risk, is obtained by comparing between those from each row. What does that mean now when you essentially try to use this now in logistic regression? And this is now where we're basically going into practicality and using this in R. So you see there on top, you see the formula or the command line, how to essentially load the data set. And you're loading it, and with the table function, you can now show exactly that 2x2 table that we have just seen before. And now we're trying to fit it. And you're fitting this with the GLM function, the generalized linear model function. You basically you set link status as our outcome. You basically using 1 to essentially indicate that there's an intercept plus the treatment. And you essentially you define the family of binomial distribution. You're defining the data set, data help.rct, and you're basically running the summary on that file. This will give you essentially these overviews. So you get now the overview of the formula, you get the deviance residuals, which essentially again shows you residuals of your estimates. Again, this is around a mean of 0, you see median. And this is basically showing you the deviation of your estimates of the model. You get the coefficients, you get, just like with the linear regression, you get an estimate for each of your covariates, including here intercept and then treatment as the covariate xi. So you essentially, you get an estimate, you get a standard error around it, you get a set value, and the probability of a set value or the so-called p-value. So the significance code indicate whether this was significant, and this is highly significant, right? So with 3 stars, with 3 asterisks, this is basically almost 0. So it's not strictly 0. Actually, since I see this already, you will develop ways how you're exporting data directly from the models, and R will set your p-values to 0. It is not 0. The p-value cannot get 0. It will never be 0, because that would imply that you're 100% certain this is a systematic difference and not just random chance that you're seeing this different. So you essentially, if you're stating 0, you actually, what you mean to say, it's something close to 0, so small that it's virtually 0. But it's formally and strictly wrong to set this to 0. So essentially what you need to do, what I would recommend to do, so say it's smaller than 0.00, maybe add a third 0, 0, 1. So that it's clear that it's really, really small, but it's not 0. Even though if you automatically export it and R sets it to 0, make sure that you are replacing that 0 with smaller than 0.001. It is just the right way to do it. Then we have the null deviance and the zero deviance. These are basically showing the degrees of freedom and the deviance of the residuals on the degrees of freedom. We have excluded 22 observations due to missingness, which is okay, not a problem. And then we have, lastly, we have the so-called AIC, that's the archaic information criterion. That's kind of, it is a marker. So you have the AIC and the BIC. These are the two most commonly used ones, the archaic and the Bayesian information criterion, AIC and BIC. And you would use that to essentially quantify its. It is not the R squared, it has a different definition. I'm not going to go into details to describe both, but it's basically, it's to some extent reflecting the accuracy of the prediction. And both are kind of equivalent good markers of this accuracy. I think the AIC is a little less sensitive towards the number of covariates as far as I recall. I usually compute both and they're usually quite close to each other. But what you can do with having AIC values for each of your models, you can basically use this to kind of build your models and get an accuracy estimate and include variables, additional covariates, and see how that accuracy gets better with the inclusion of each variable. And then have your inclusion of variables driven A on hypothesis. It's always important that you have hypotheses that drive your variable selection. And B, you can then look at the change of AICs over each iteration of that model, and you essentially can then have that drive your decision of whether to include this model or not, or include this covariate in the model or not. Okay. Excuse me. So essentially, if you want to quantify the odds ratio now, you would need to winter's coming. So we have fit coefficients of 2. This is so if you look at fit coefficients, you basically get the estimate, and you are essentially getting the treat variable. You exponentiate this, you get 6.77, just exactly as the one we calculated here. So logistic regression does allow for you to quantify the odds ratio just in the same fashion you would do it in a 2x2 table, and it's usually quite accurately reflecting the odds ratio. So this logistic regression model essentially shows now log pi over 1 minus pi equates to the covariates on the right-hand side. Yi is here a binary outcome that essentially is your pi. Xi can be a binary categorical variable, polytomous categorical variable, or a continuous variable. It's non-discriminative what shape or form your parameter is. For the R programming, it's a little trickier because you need, if you have a polytomous categorical variable, you need to transform it in a factor, just like we did in the past. If you have a dichotomous, it's easy. It's a 0 and 1. Makes the interpretation also easier. Then it also can be numerically, by the way. But I wouldn't recommend it because then it gets a little tricky to remember what you have done. I would always transform it in a factor. And for a continuous variable, interpretation is a little different. So essentially, when you have xi as a continuous variable, your exponentiate beta 1 can be interpreted as an odds ratio to have the outcome, which is a disease, flu shot, vaccination, whatsoever, with 1 unit of increase of your xi. And this will be an interpretation that is consistent with later occurring regression models that you may be seeing, like Cox proportional hazards model or Cox regression essentially is also to be interpreted in the same way, but more about this in BIOS2. Okay, so we can extend the simple regression to the following multiple logistic regression model. And this is now where it's really getting interesting. Because when you think about it, it's usually not just one covariate that you're interested in. It's not just one covariate that will predict the outcome. So if you are looking at the outcome of hospitalizations, it's not only age that will predict that outcome. Or when you do systolic blood pressure, it's not the serum glucose alone. It's also the age, it's the gender, it's, I don't know, smoking habits, atherosclerotic events, blood, hereditary blood pressure diseases or conditions, which people have higher blood pressure to start with. Also with genders, like women have lower blood pressure compared to men. What else? Alcohol intake, classic. Smoking, we had drug use, classic. Or things that affect your outcome variable. Okay, I'm talking now about the continuous outcome, but basically you would need to stratify it first to get a binary outcome, obviously on the outcome side. But these are just, you want more confounders to be included in your models. So for that very reason, you're basically approaching it in the same fashion as you would approach it in your multivariable linear regression. So you add additional covariates, and the interpretation of each of these is the same as we have here. So basically you get each continuous variable will show you the odds ratio with 1 unit increase of your xi, all else being equal. And this is one of those phrases that you will often see whenever it comes to reporting of logistic regression. You will hear all else being equal. And this is how you can interpret it. If you want to have the overall odds ratio of one individual, you can even calculate, you can do it in the same fashion as we did it for the linear regression. You can use each of the covariate and the intercept, and you can calculate the odds ratio for one individual. So you have, for example, you want to calculate the odds ratio for an individual that's 37 years old, is a smoker, is a drug user, but doesn't drink alcohol. You can do this, well, unrealistic example, but you can essentially do this and calculate the odds ratios of this individual being hospitalized for myocardial infarction, or having myocardial infarction, or having high blood pressure as a binary outcome this time. So you can essentially do all of this. So this is confounding based modeling. So this is, you basically, you think of the confounders, and I highly encourage you to always map those out in a directed acyclic graph that you will learn in your epi classes. Using DAGs will allow for you to essentially map out relationships and will allow for you to determine the right covariates to include in your models to essentially get to building models that really have a high accuracy in the predictive qualities. So the beautiful thing is we do not have to check for normality We do not have to check for Bernoulli distribution, so that's nice. And we also don't have to do a constant variance check because essentially that falls off with a binary outcome, right? Okay, what else? Then we also need to interpret the estimates. So beta one essentially is our beta one hat is now our predicted log odds. And this is in terms of nomenclature, these are considered log odds. Only when you exponentiate them, you get to the odds ratio. So exponentiated beta one hat will get you to the odds ratio of 6.8 for our link status example. What we also see here is essentially the 95% confidence interval. Also, this can be extracted easily from the model, and we can then report our odds ratios exactly in that shape and format as we have shown it here. So we're comparing to the untreated as expected. The people treated are more likely to link the primary care with an odds ratio of 6.8 with a 95% confidence interval from 4.3 to 10.6 with p-value of less than 0.001. And this is how I want you to depict that and to state that it's less than 0.0001. So indicating it's very small, but it's not zero. Although R set 0, right? Remember this? R says 0. So when you extract that p-value, R will give you 0. Make sure that you're replacing it. Yeah, that's the same. That's essentially the same model as before. And that will really allow for you to depict it, right? What's nice, so since it's a ratio, so this is treated yes, no, as a ratio, what will be the default where you basically do not see a significant difference? Logically, it has to be because it's a ratio, it's a 1. So if you have the same odds in either group, treated or non-treated, your odds ratio will by definition be 1. So only by transforming it, so it's now from 0 to 1, you're basically using the log odds to basically relate the log odds to the probability. And excuse me. No, it's getting humidifier time. So essentially, you have you're relating the log odds to probabilities, and you essentially you look now in transforming something that is limited by 0 and 1 to something that is ranging from -infinity to +infinity. So essentially, where these log odds meet is at 0, and an exponentiated 0 becomes 1. And it's also in terms conceptually, when you have a ratio between I don't know, the risk of myocardial infarction in men and women, risk divided by risk, you basically get a ratio of 1. And this is a neutral risk difference or risk ratio or odds ratio. Okay, but that's quite obvious and you have done that in previous classes. So what this means is your 95% confidence interval does indicate whether there's a significant difference. So that p-value is essentially redundant information. A lot of journals will essentially ask for you to not even include the p-value because p-values are over-reported. It's really more elegant to include 95% CIs because they also indicate some marker of the variability of the actual estimate. And this is much more valuable information. Good. What are we doing now with the intercept? The intercept beta hat 0 is -1.6. How is that to be interpreted? So again, we're coming from log pi over 1 minus pi. We're coming from beta 0 to beta 1. We are essentially transforming this now. So the beta 1, beta 0 and beta 1 estimated from beta hat 0 and beta hat 1, we could calculate the probability for the occurrence of the outcome at any value of xi. So the beta 0 basically gives you to some extent the default status. It's like your default estimate. This is your intercept. This is what the probability in the context of the HELP RCT data, it's the probability to link a primary acquisition in the untreated group, no treatment, and this is like default, this is the baseline. This is basically your untreated, naive kind of population. This is the interpretation of the intercept here, where xi is 0. And that's essentially, that's where I'm at the end. I hope that was all kind of clear. Logistic regression is a very important method, so I'm really highly recommending you study this carefully, and you also pay close attention to the lab and play with the lab around to make sure you're really solid on this concept. So essentially, it is. It will allow for you to perform many analyses that essentially can answer many research questions, so keep that in mind. Okay, so see you in the lab, and I'm concluding logistic regression in theory here for the lecture, and yeah, post questions to the discussion board. Let's have a conversation about it if you're interested in anything more specific with my insight. All right, so see you in the lab, and hope it was insightful enough. Post questions. All right, bye-bye.